Today's training, the first one of our series, is on the development and end of life of rigid bio-based plastic packaging. We have today with us two of our project partners and experts on the topic, obviously, from SABIOMATERIALS and Logoplaste. I will be introducing them in a second. Therefore, just in a nutshell, within this training is within this framework of the EU-funded project, BioSupPack. This project is funded by the former Bio-Based Industries Joint Undertaking, now called the Circular Bio-Based Joint Undertaking, and the Horizon 2020 program. BioSupPack stands for Demonstrative Process for the Production and Enzymatic Recycling of Environmentally Safe, Superior and Versatile PHA-based rigid packaging. As you know, as you've seen, this is about, indeed, rigid packaging, this training, and we have two experts that have been taking care of the development of these responsibilities within the project. Sorry, I am letting people in the chat. Welcome to those who have just joined. Just as you have done, please keep yourself muted, and we are about to start. So a little disclaimer. This is funded by the European Union. The views and opinions expressed are, however, those of the authors only and do not necessarily reflect those of the European Union or European Bioplastics. Neither the European Union nor European Bioplastics can be held responsible for them. This is our little disclaimer that we always have. And the structure for today, we have one moderator. That's me. I am Estela Lopez Hermoso, EU Project Manager at European Bioplastics, is one of the partners in this project, and we are responsible for communication and dissemination in the BioSupPack project. We have two speakers that we will be speaking during 60 minutes, 30 each, one after the other, and we will have then a Q&A session for around 20 minutes, and after that, we will let you go. But before we'll share with you the link to an offline test for the completion of training to be able to have your certificate of training. So this is a part of a series of specialist trainings, as I've said, and you will receive this presentation and you will have then all these dates that you will be able to check. Please keep yourself muted when you enter in the chat. That will be great. Thanks. And then you will have all these other sessions that you will be able to follow with the same structure and the same principle. Excuse me, there is a printer going on behind me, and I hope you are not hearing a lot of noise. Then, some housekeeping rules, please. No AI tools are welcome. No recording should be made. This training is really right now being recorded, and we will share with you the recording in due time as well with the presentations. During the training, please keep your microphone on mute and your camera switch off as you're doing now. Thank you. And we will be taking questions after the presentation of the experts. We will have one presentation first and another one right after that. So you can use the chat to write your questions as the moment that you have them, and then we will pick them all up during the Q&A question. So now our first expert, Michele Rossi, as you can see from SABIOMATERIALS, he has a degree in chemistry and he holds a master's in chemistry and pharmaceutic technology from the Università di Bologna. And his professional experience is a material developer at SABIOMATERIALS, specialized in design and preparation, melt mixing of bio-based and biodegradable materials. He manages materials characterization like analysis of mechanical, thermal, and physical properties and sustainable end-of-life legislation. We also have Pedro Santana from Logoplaste Innovation Lab, who has a degree in mechanical engineer from the Universidade Nova de Lisboa, and education in advanced product quality planning, product development management, and methodology HD. He's the head of R&D funded projects at Logoplaste and has ample experience as project and program manager in the R&D in the fields of recycling, circularity, and bio-based materials, and industrial engineering and design. As you can see, these are very thorough experts, and they will tell all about the development of the rigid plastic packaging and end-of-life of this packaging within the framework of the BioSupPack project and what they've been working on. So without further ado, this would be afterwards. So Michele, I pass the screen to you.
Thank you very much, Stella. Thank you. So in the middle of my sharing, I would like to briefly introduce again myself. I'm Michele Rossi. I'm a chemist. Even if I have a background in pharmaceutical chemistry, but I'm on board in the dark side of the chemist from more or less 6 years, and because I'm in SABIOMATERIALS more or less from 6 years or maybe 7, I don't remember well. If you see my screen now.
Yes.
Yeah, great.
Thank you.
And this is the first specializing training for this session, and is based on the development of end-of-life of rigid packaging, bio-based plastic packaging. These particular 2 case studies has been developed inside of BioSupPack project. BioSupPack project, as Stella said before, is a founded project in the 2020, where the main aim of this project is to find an alternative bio-based renewable sources for production of new bio-based material. In that case, the focus of this project is found a solution to produce alternative polyhydroxyalkanoate by using different sources. In that case, has been selected brewery spent grain as a waste of industrial of the beer, that permit, after the fermentation, to produce polyhydroxyalkanoate, in particular PHB, that has been used, studied, and developed new material based on this thermoplastic material, thermoplastic polymers. In particular, SABIOMATERIALS is a part of this consortium of companies and research center. And the role of SABIOMATERIALS, essentially the main activity of Sabio is the production and design of new bio-based thermoplastic material. We are located in Italy, we are located in Forlì, and we are specialized in combining different material, raw material, for the production of bio-based and biodegradable polymers. So our main activity is the formulation of new material that permit to obtain a different kind of article at the end. We are in facilities that is in Forlì, is more or less 1,050 square meter as a productivity area, more or less 500 square meter between office and laboratory. The equipment for the production of material is characterized from 2 different extruder, 1 pilot line and 1 extruder for industrial scale up, and producing material in very larger scale. Single screw extruder that permit to produce different prototype and articles that could be directly sold to our customer, and then injection molding machine for the production of specimens. Laboratory typically equipment as a plastic industry, means dynamometer, rheometer, oven, scales, and scales equipped with density kits. The main portfolio of material developed in Sabio, SABIOMATERIALS, are essentially 3. The first part, the first main business of SABIOMATERIALS is related to materials that could be used in agriculture. We have developed Terralix, a material that's received the biodegradation in soil. Material for packaging, and here has been created Biodegra. Biodegra is a grade typically used for packaging. And the last part is the material used for rigid and durable goods. For example, Biodura is a material that permits to obtain material for high-end items with long life of use. For example, chairs, for example, durable goods, durable items. More in detail, SABIOMATERIALS produce the material called Terralix. It's a soil biodegradable material for agricultural application, with the aim is not to release microplastics. This material present a certification of soil biodegradation in soil from the certification to Austria. This is very nice because we try to eliminate the release of plastic in the soil, and with an alternative of this material that could be biodegraded directly in the land. The second material is biodegrad. Biodegrad is typically used for packaging like film or bottles, for example. The end of life is completely different because in that case is useful to be compostable in industrial and home condition. In this case, we are waiting the certificates or to receive the home condition for composting. Last but not least, Biodura. Biodura is the material for rigid and end-of-life packaging with a very added value for this final product that could be obtained from Biodura, but Biodura is a material for durable goods that derive essentially from bio-based resources. Bio-based resources means resources that not are related to petrol, and in this case, it has been possible to obtain by using this material a full body chair, or on the right side here, you can see this bottle display. This bottle display is something that has been developed in BioSupPack, in the project of BioSupPack, and SABIOMATERIALS have the possibility to develop a new material that permit to use the polyhydroxyalkanoate produced inside of the project BioSupPack for the production of this durable item, a bottle display for beer. For beer, that's deriving the sources from the same company, the company that's producing the brewery spent grain that converted in polyhydroxyalkanoate has been used for the production of material for, at the end, the first user. So here we can see the two case studies that SABIOMATERIALS hit during the project. The first one is the production of material for injection molding prototype for rigid packaging. So by using polyhydroxybutyrate from the project with different specific property, for example, rigidity of the material, fluidity that will be better studied inside of the case study. And the second case study is related to their potential end-of-life options, means the mechanical recyclability of the article, the final beer display that we have obtained. So, goes into detail, the first case study has been the production of material for injection molding for prototype, like a rigid packaging for beer display. The available information, and this is a typical way that SABIOMATERIALS approach to a new project and approach to the development and design of new material, is typically a production of a description packaging sheet. This description packaging sheet is an example of a number of questions, a number of requirements that we ask from customer, or in that case of the partner in the project, to be filled with all the information that could be very useful for the design of the material. In that case, after the evaluation of the description packaging sheet filled by our partner, we found some requirements very important. The first one for sure has been the possibility to use polyhydroxybutyrate for the production of the final article, the use of the new material based on PHB through injection molding facilities for the production of the beer display, the possibility to be part with relief embossments, so present some aesthetic possibility to be added to the beer display, and also the resistance of the new beer display, so have to resist the weight of 2 or 3 beers on the shelf, for example. Everything seems at the beginning, very complicated because we don't have any kind of term of comparison with other plastic, for example, because at the moment the beer display has been done in cardboard, so we can't produce a new material based on cardboard. And again, we don't have any kind of technical data sheet to copy or have a correspondence of data, so we are totally blind in this case to produce a new material. So in this case, probably this slide is very important. It's one of the most important slides because it's the example how we design internally the material. We start from the requirement. For example, material for injection molding is one requirement, and we would like to have a correlation with a material property. Typically, material for injection molding present a very high fluidity. So for the design of the material, we took in consideration to have an high met volume rate. We base on this technology, the material of use of polydroxybutyrate, PHB, so the content of PHB should be higher, the maximum as possible. The possibility to be aesthetic inclusion and relief or embossment seems the property should be high polarity of the surface, and it is very easy because PHB present a good surface polarity. So this is not a parameter that we have to too much take in consideration. And resistant to support 2 or 3 bears. So this means that the final material should present a very good rigidity. So taking consideration of several parameters that we have identified from the requirement, we made some tests of material formulation, passing through the material preparation to the injection molding for the formulation, for the realization of the dog bone specimens, and at the end for the first analysis that permit to determine a series of compounds that you have obtained based on polydroxyalkanoate, PHB in this case, that could present essentially a couple of requirements, means fluidity and flexural modulus. In that case, you can see that we have used commercial PHB. The use of commercial PHB has been due to the fact that it's been difficult at the end of the project receive PHB that derive from directly the BSG. So for the first analysis and the selection of the better composition has been better to starting with commercial PHB, commercially available PHB. Keeping in the formulation the material properties that, as we say before, high quantity of PHB, rigidity, high MVR, and also shrinkage, that is another properties, so very low, 1 and 1.5, between 1 and 1.5, to permit the exact extraction of the final article from the injection molding. Here you can see an example of 6 compounds that we have obtained. We have obtained more or less 30 compounds, but here has been to facilitate to show only the best compound that we have obtained. But from these 6, only 1 should represent for us a very good material because present all the characteristics or the first characteristics, the first request for the technology, means an higher met volume rate and 180 degrees with 2.6 kilos is 13, is the maximum that we have obtained. And also the flexural modulus is the higher that we have obtained, 4017. The main ingredient for all this compound is PHB. The rest of the ingredients are aliphatic biopolyester that permit to formulate a potential compound useful for this application. Based on the first analysis, we permit to select and reproduce in larger scale the compound SABIOBSP06 and finally characterize for a full thermal mechanical properties. In this case, you can see that the density is very higher, 1.34. The MVR, as I said before, is around 13. Is very important is the number of rigidity that we have maintained 4017. The PHB content is around 60%, but we saw also potential in very interesting data. This means the stress at break very high, close to 35 megapascal, and also the elongation. We do take in consideration the elongation is typically not very good because it's only around 4%. But regarding the final article, a beer display that do not have a stress of elongation during their life, this parameter for us is not be took too much in consideration. So 4% is enough. What is important is the rigidity and the strength of the final material. So in that case, the number obtained are very good. For the production of the prototype, we have also indicated some guidelines for the injection molding, how to set the temperature. And as you can see, a figure of typical temperature profile. I would like to point your attention regarding the temperature used, where typically present temperature profile that start with a lower temperature until a higher temperature, but to facilitate, in this case, the injection molding and the cycle of time for the realization of one single piece, we found that it's better to start with higher temperature in the first zone, closer to the feeding zone, and decreasing the temperature along the screw of the injection molding. This is a typical inverse temperature profile, keeping the material inside of the mold at temperature of 45 degrees to facilitate the crystallization of the material. Based on this experiment, we passed to the scale up. So scale up of the formulation. So not anymore 3 kilos, but moving to 25 kilos and by using the PHB from the project. So we changed the source of the PHB, not anymore from commercial, but from PHB from the project obtained from waste. In that case, we received the material, the PHB, and here has been the first challenge. Before the PHB commercially available was in pellet form, the reactor grade is not anymore in pellet form, but is in powder form. Powder form is more challenging to be used, to be weighed, and to be for the preparation and for dosing for the extrusion. So we have to keep in consideration that organic powder is typically not very welcome in company, in plastic or bioplastic company for the preparation of material, due to the fact that they are difficult to be feeding, to be dosing, and also could be toxic sometimes for skin, for length. So everything must be very safe to use by using all the DPI, as you can see here. So after the preparation of the material, there is also the challenge of to dosing and feeding the extruder, because most of the time it's very difficult that a powder should be very precise and homogeneous dosing. We change a different screw from the dosing until that has been the possibility to find the correct form of the screw for keeping homogeneous the extrusion. In this case, you can see that the material goes out from the extruder, a twin screw extruder that presents 5 filaments, goes into a bath of water, and at the end is cut in the air for the formulation and formation of the pellet as a final form. The productivity is around 21 kilos per hour. This is our pilot scale that permits to work for several hours. And at the end, we have obtained also in this case 25 kilos, but by using the same formulation developed before, but changing only the source of PHB. Again, the creation of the specimens, the dog mold by injection molding, and finally the comparison between the two materials. The material obtained from commercial sources, commercial PHB, and the material, the same material, but only changes the source of the PHB. So for both, the percentage of polydroxybutyrate represents the same value, 60%, because it's the same material. The density changes a little bit, only the last digit, but this is not most important in that case. What we would like to would be maintained is the fluidity, because at the end we would like to obtain the final article. So the fluidity is a parameter that for us is very important to be keep it the same, or at least better, and in this case is 14.3, so more or less the same at this the value, and also the rigidity could be maintained as the same number. As you can see here, the number is more or less the same. We lost something in elongation. This is probably due to the fact that the polymers that we have obtained in the project present a different molecular weight compared to the commercial one. But in any case, all the material properties that we have detected from the Young modulus, the stressed break, and also the flexural modulus, for us represent a good starting point to say that the material obtained inside of BioSupPack are very similar, is very similar to the PHB commercial available. So in conclusion of this first case study, the renewable sources like brewery spent grains represent a promising feedstock to produce PHB. The material obtained BSG 11 material is a good material because presents more or less the same material property compared to the 06, and the production in larger scale has been done very easily, taking consideration some tricks, but has been very well done, obtaining 25 kilos. Following this first case study, a second case study has been done by, in this case, evaluating the potential recyclability of this material. With this in mind, the aim of this second case study is the validation of a post-industrial scrap, means parts of during the process of formation of the prototype of the beer display could be recovered through a mechanical recycle. In this case, we would like to evaluate first a characterization of the reintroduced PHB-based material pre-consumers, so a mechanical recycle scenario around 100% of the recycle. This means the product obtained during the production of the bottle display is not commercialized yet, but remain inside of the company who produced the beer display, and being this material out of specification or present some parts not very well released, very well done, could be remilling and reintroduced in injection molding process for the production of new beer display. The second experiment has been the possibility to recycle a different percentage, 30, 60, and 90%, and try to have the possibility of analyze a mechanical recyclability scenario of typical industrial company after post-consumer. So for example, the beer display has been damaged during their life, and a waste manager could collect this material, this article, and could be reintroduced in a mechanical recycle scenario to validate the possibility to be recovered mechanically. So first of all, the first things is to collect the post-industrial scrap produced during the demonstrator prototype production. As you can see here, an example of industrial scrap where parts of the beer display is not being completely very well done during the extrusion. These parts here are the typical first injection where we are setting the best condition for the production of the prototype. So after the collection of these off-spec prototypes, the second activity has been reducing the size, so milling through machinery that permitted to destroy completely the form of the beer display in small pieces, small fragments. More or less, we found that the best particle size is around 3 millimeters, because this dimension permitted to be feed and dosing very homogeneously in our implant. So first analysis has been the characterization of a PHB-based material consumer. So a material that directly will be reintroduced in injection molding, and the scrap could be used for the production directly of a beer display. In that case, we made the same. So we have reintroduced the post-industrial scrap milling inside of the injection molding and obtaining in this case the specimens directly from the scrap, so 100% of recycled material. Here, more or less, you can see the setting used for obtain the specimens, a cycle, total cycle time 30 seconds. The temperature setting is 117 in the first zone 1 and 2, where the material is typically melted, compressed in third part of the screw of the injection molding, and the nozzle at 150. Also in that case, we found that the inverse temperature profile represents a good solution to obtain the specimens. In this second picture here, some parameters of pressure and speed of the extruder, speed of injection, post pressure, that permit to guarantee to obtain a compact without bubble inside specimens, that to not avoid some problem during the characterization. The second example of material recycle is to obtain a different grade of material that present inside the 30, 60, and 19% of recycled material. In this case, we have analyzing a scenario of post-consumers, so waste management, as I said before, manage this, the material will be scrapped and reintroduced in a formulation at different percentage. So in that case, we have introduced a different percentage of post-industrial scrap after demiling internally of virgin material, essentially inside of Sabio BSP 11. In this case, it's not possible to introduce the material directly in the injection molding, but we pass through an extrusion. Means we move 30% of the material recycled, and for example, the 70% of virgin material, 60% of recycled material and 40% of virgin material, 90% of recycled material, and only 10% of virgin material. This combination here has been reprocessed in extruder, obtaining the pellet, and only at the end produced the specimen, just to analyze the potential lost or keeping the same property of the virgin material. A table of comparison. On the first green column, Sabio BSP 11 is the material obtained before, and the following 3, 30, 60, and 90% are the characterization of the material with different percentage of recycled material inside. The last column is the 100%. For all of these materials, more or less, the density is keeping the same because the formulation used is always the same, even for the PHB content is keeping and maintaining the same value. What is changing in this case? For sure, the fluidity. The fluidity goes up, increasing the quantity of recycled material, starting for 14.3 for the virgin material and moving to 20 for the 30%, 23 and 28 for the 90%, until 55 for 100% of recycle. This means that the possibility to reintroduce at 100% in a formulation, in our opinion, also considering the rest of the property, do not represent a very good idea to recycle the material. Should be very good and very better that a waste management company present the possibility to reintroduce a recycled material, maybe in a different percentage, around 30 or maximum 60%, because the material property detected are very similar to the property of the material in virgin condition. So BSP 11, yes, 11. Also for the rigidity, as you can see, is more or less keeping the same value, maybe a little bit decreasing for 30%, 60%, and more or less the same value for the 90%. Also, the stressed break is something, is a number very similar to what we have detected. What is decreased a lot is the elongation. Starting from 3.53 obtained at the beginning, we lost quite completely the elongation. Most important, as you can see here, for 100%, we are around 1.28, so quite nothing elongation. But it's maintaining similar the flexular modulus around the same number. We saw a decreasing of the value, probably due to the fact that higher recycled content inside of the formulation means a lower molecular weight inside of the formulation, so we lost some properties for the flexular modulus. So how can we conclude in this case? After the recovery of the post-industrial scrap and the miling, that is a typical process and is very easy to be obtained, the material obtained has been also easily injected, and for the result that we have obtained after the characterization, we can suggest that only the 30% or 60% of the recycled material could be suggested to a potential waste management regarding the reintroduction of scrap of bio-based material based on polyhydroxyalkanoate, in this case PHB, for a material recycled. We suggest to avoid the 90% and 100% of recycle due to the material property that we have detected. And also, we can see that our mixing strategy permitted to represent a good strategy for the recycle of new bio-based material that's derived from renewable feedstock. So this is more or less all the data or the activity that we have done. In case of question, we can wait in the second part of this training. And now I would like to leave the stage to colleague Pedro for the presentation. Thank you very much for your attention.
Thank you, Michele. And while Pedro looks for his presentation, thank you very much. I remind participants that, as Michele just said, you can write your questions in the chat so that you don't forget, maybe, and then we will pick them up again after Pedro's presentation. Okay, and then you can either put them yourself, or I would be reading them, and everything is being recorded. But the Q&A will be off afterwards. So Pedro, you have the screen.
Yes.
You can share whenever you want.
Just a minute. Can you see my screen?
Yes.
Perfect. Yes, perfect. So, good morning, everyone, and thank you, Michele, thank you, Stella, for the presentation and introduction. So, as Stella mentioned, I'm Pedro Santana. I'm the responsible for the funded project of Logoplaste Innovation Lab, and I will try to give you some insights about Logoplaste experience with the funded projects in which we try to leverage our knowledge in this kind of new materials and new solutions that we think that might be the solution for the future for packaging. So in this presentation, I will start by giving you a short overview of Logoplaste Innovation Lab, and then I will move to our experience with biopolymers, and in the end, I'll try to give you some insights about the end of life of rigid bio-based packaging. So regarding Logoplast, the company has 67 factories worldwide, of which 88% are entirely dedicated to specific clients. Of these 67 units, 64% operate under what we call the wall-to-wall model, meaning our facilities are integrated within our clients' facilities, allowing packaging to be delivered directly through a wall to the production line. We are present in 18 countries across 3 continents, employing around 2,600 people, among other key factors, as you can see in this slide. As for our packaging, we use an average of 22% of recycled materials, and additionally 35% of our energy comes from renewable sources, and most of our packaging is fully recyclable. With these numbers, we avoid the emission of approximately 22,000 tons of CO2 each year. This is basically the business model of Logoplast. As I mentioned on the previous slide, we are present in 3 continents and in 16 countries. And as you can see, our main markets are the United States and basically Europe. Within our portfolio, we offer packaging solutions for a wide range of market sectors, from personal care in its many forms to the health and pharma, home care, and dairy segments. We also operate in the food contact sector, covering a broad spectrum of applications, from sauces and water to beverages and spirits. Within these segments, we work with a wide range of partners, including the leading players in their respective markets, such as Kraft Heinz, P&G, Unilever, and many others, as you can see in this slide. So finally, regarding Logoplaste Innovation Lab, or iLab as we call it. Given the technical challenges and the level of support required for packaging development, it became necessary to create a specialized department within Logoplaste structure. And iLab takes an agnostic and holistic approach to both technologies and above all materials, naturally including emerging solutions such as biopolymers. Our mission is to develop tailor-fit packaging solutions adapted to the needs of our partners and the packaging ecosystem while considering all variables of the innovation process. At iLab, it's headquartered in Portugal, in Cascais to be more precise, and supports 2 additional development hubs. One in the United States, our largest market, as I mentioned, where being close to our partners, it's essential for our business, of course. And another hub, it's located in the United Kingdom, in which we have also a strong presence. For all the other markets, iLab Portugal gives the necessary support, including the funded projects as BioSupPack. As I mentioned, iLab and Logoplaste take an agnostic and holistic approach when it comes to the technology and materials used in the development and production of packaging. And taking that into consideration, our development process is based in 4 key factors. Human factor is the starting point, and it's always necessary to understand what people truly need, and this factor remains at the core of any packaging solution developed by iLab. The technical factors, and in which we assess whether existing technologies can meet both human needs and the demands of the packaging ecosystem. The business factor, of course, any solution must be scalable and financially viable to ensure its sustainable implementation. And finally, we have the biomimicry factor. It's very important and key tool that we apply in our package and design process, in which we are inspired by the nature principles to create more efficient and sustainable solutions. With this in mind, we have acquired and developed a comprehensive set of skills that enable us to have all the necessary tools for packaging development. This process covers everything from researching new solutions and defining specifications in collaboration with our partners, through design and engineering to full industrial implementation. In addition, we ensure certification, regulatory compliance, and conduct recyclability studies, guaranteeing that our packaging meet expectations throughout its entire life cycle. Now, moving on to the iLab experience with biopolymers. I choose to highlight the BioSupPack project, of course, not only because it's directly related to this workshop, but also because it serves as an excellent example of a project that goes through all the typical stages of developing a new packaging. In this project, one of the main goals is to develop rigid plastic packaging, bio-based rigid packaging, to demonstrate that polymers derived from brewery industry waste represent a technically viable alternative to fossil-based plastics. As part of this effort, rigid monomaterial bioplastic packages were developed with their performance will be optimized through plasma treatment to improve barrier properties. The case studies considered in this project included 2 cosmetic packages, one for home care and 2 cosmetic packages, one for home care and finally one for food contact, especially a packaging solution for a food sauce in the case of the food contact. For cosmetics, we will have sunscreen and body peeling packages, and for home care, we have a fabric wash liquids package. So the first step in the packaging development is to define the technology that will be used with the goal of validating development concepts that can later be scaled up and to an industrial reality. In this specific case, and considering the iLab experience with the materials developing in the project, the chosen technology was extrusion blow molding process, in which you can see here in this video. In general, the process begins by feeding plastic pellets in a melting screw, where the material is, sorry, let me put it again, in which the material is heated until it reaches a semi-molten viscoelastic state, and then the material is then compressed through a die and mandrel assembly and extruded in the form of an hollow tube, as known as a parison. When the parison reaches the desired length, it's clamped by the mold, sealed at the base and kept open in the neck area. And then through this opening, blow pin injects air into the parison, causing it to expand against the walls of the mold cavity, where it cools down and takes its final shape. Finally, the pinch areas where excess material accumulates are trimmed off, and this material can be also reused and reintegrated directly into the extrusion process. To give you a sense of comparison about the PHA, that it was the goal of this project, and the standard materials. One of the most critical factors in transforming plastics into packaging is the temperature profile during processing and the operational window of the material. In this case, in the case of conventional petroleum-based materials, such as HDP and PP, extrudable molding equipment is typically optimized to operate at high temperatures, as you can see in the slides, way higher than the BR polymers. However, when these same conditions are applied to the alternative materials, such as certain grades of PHA, the extrusion of parents can become very unfeasible, as you can see here in the image. You can see that the material is quite fluid, and it was impossible to form a stable and blowable comparison. In parallel, it's essential to consider other critical factors related to the characteristics of the material, such as the melt strength, flowability, and once again, thermal stability. Other important aspects include the barrier properties of the material, of course, and their shrinkage, a key parameter in mold design and manufacturing. Additionally, certain intrinsic effects of the extrusion process itself must be taken in account, such as sagging, the sagging effect, which refers to the stretching of the parison under its own weight, and swelling, a phenomenon in which the material expands after extrusion. Finally, for effective packaging development, it is crucial to consider the tooling characteristics of the equipment, as well as the specification of the packaging, including the required mechanical performance and dimensional stability. Namely, very important for the neck, considering that we'll have the enclosure on it. These factors ensure that the packaging remain fully functional throughout its entire life cycle. That was precisely the case of all studies carried out within the BioSupPack project. Based on the specifications provided by the end users partners, the characteristics of the materials and the equipment available for the EBM trials at iLab pilot facilities, the PHB packaging was initially designed and modeled using CAD software. After the designs were approved, the process moved on to the validation of mechanical performance, including the theoretical calculation of the minimum average wall thickness required to meet the specification top load requirements. In this specific case of the SunCare packaging, an average wall thickness of 0.5 millimeters was achieved, with a total weight of 17 grams, ensuring a minimum top load of 100 newtons. These values fall within the capabilities of the available equipment and are consistent with the typical parameters of for packaging of this type. The same methodology was applied to the remaining packages or case studies of this project. In the case of the body peeling packaging, a slightly higher average wall thickness was obtained, even though the package was quite similar to the previous one. Nevertheless, the results remain within the acceptable limits for both the technology used and the specific type of packaging in question. The same for home care packaging. And here you can see that due its larger dimensions, higher top load specification was expected. However, thanks to its favorable geometry, it was possible to achieve an average wall thickness similar to that of the previous case study, while still meeting all the defined technical requirements. And finally, the sauce packaging case study presented a particularly interesting result because although it had a less demanding top load specification, the average wall thickness obtained was once again similar to the ones before. And this outcome is mainly due to the bottle's geometry and or design, especially in the neck area where there is an almost horizontal section here. You can see here with a relatively tight angle. This configuration causes stress concentration, leading to a failure mode under relatively low loads, even when the wall thickness is adequate. In here, you can see that small details of design can lead to very underperformance packaging. For that reason, the importance of using tools such as finite element analysis, as well as the critical influence of the design engineering on the structural performance of packaging throughout its life cycle. The next phase, and with the designs finalized and validated, the next step was to the production of the molds and tooling necessary to validate the concepts and materials developed throughout the project. In this context, two materials were tested, the first being SABIO BSP13, and however this material delivered results below for its technology, it was showed some success in extrusion blow molding tests conducted in a laboratory setting in IMPLASH facilities, another partner of this project. But in iLab's trials, it underperformed quite severely. We couldn't get bottles, and as you can see, the material behaved in a very strange way. It became very fluid or very degraded, and it didn't show any kind of swelling, and it showed a very excessive sagging. It became very sensitive to the processing temperature, and that's the reason for this behavior. Following the, I would say, not positive results with the previous material, testing proceeded with a new grade, which showed a significant improvement in behavior during parison formation, as illustrated in the video. Despite this improvement at materials, the material's high sensitivity to elevated temperatures remained evident. On this specific machine, there was a safety limitation preventing the use of temperatures below 160 degrees. This is a safety feature that is typical in industrial machines, which corresponds to the upper limit of the typical processing window for pH. In addition to the thermal sensitivity, excessive sagging and lack of parison swelling were once again observed. Nevertheless, it was possible to produce a few packaging samples for the cosmetic case studies, although these were not considered viable to the visual and functional defects that affected their overall quality. As you can see, the defects observed in the packages produced within the second material can be summarized across several critical points. There was a lack of uniformity in material distribution along the bottle, with thickness variations that compromise structural consistency. In addition, poor adhesion was detected in the pinch-off and trimming areas, which could affect both the seal integrity and overall finish of the package. During the melting and extruding stages, insufficient material adhesion was also observed, making it difficult to achieve a stable Patterson formation. Finally, damage occurred in the area where the blowing pin was removed after blow molding, leading to imperfections around the neck area and compromising both the aesthetic quality and the functional performance of the packaging. The same situation occurred with the cosmetic bottle for body peeling. Since this packaging has a geometry very similar to the sun care, the processing challenges were almost identical. Once again, issues such as the non-uniform wall thickness, poor adhesion in the pinch-off and trimming areas, and difficulties in material fusion and extrusion were observed. As in the previous case, defects were also visible in the area where the blow pin was removed, compromising the final quality of the packaging in both appearance and performance. In other words, and after the initial trials and processing attempts with the materials developed in the project, it was concluded that these materials are extremely sensitive to temperature profiles, displaying a very narrow processing window. Even small temperature increases lead to a rapid material degradation, making it either overly fluid or brittle. This instability compromises the process consistency and highlights the limited capability of these materials with the current industrial equipment and tooling, which are designed for conventional oil-based materials. Now, finally moving to the end of life of rigid bio-based packaging. I will briefly address the end of life of the bio-based packaging, beginning with the regulatory framework, particularly the PPWR, and what it establishes regarding compostable packaging. The regulation clearly identifies the types of packaging that must mandatorily be compostable. This includes, for example, permeable tea bags, coffee capsules, bags for fruits and vegetables, basically situations where the non-consumable organic content exceeds the weight or volume of the package itself. In such cases, the packaging must be compostable in accordance with the standards for industrial composting, and when required by a member state, also in compliance with home composting standards. This requirement is expected to come in effect 3 years after the official entry in force of the PPWR. Additionally, regulation allows that some member states may permit or require that other types of packaging can only be placed on the market if they are compostable, with the practical implementation depending on the specific requirements established by those individual states member. Basically, for all these directives to be effectively implemented, it is essential to clarify and standardize the various materials, which requires defining some key characteristics. First, the term bio-based refers to materials derived from biomass, meaning renewable biological resources. In contrast, biodegradable materials are those that decompose through biochemical process in which microorganism presents a given environment convert the material into water, carbon dioxide, and biomass. Finally, compostable materials are subset of biodegradable materials, but they meet specific criteria that allow them to be composted under controlled conditions, either in the industrial composting facilities or when applicable through home composting. Finally, regarding recycling circuit of biopolymers, it presents several challenges, starting right at the collection and separation stage. Although technologies are available, there are still no established or few established streams for biopolymers, since their development depends on the amount of material available. That is, of course, a problem these days for collection and recycling. Thus, this is not enough scale, of course, to make the process economically viable. Furthermore, most of the materials currently available for recycling comes from post-industrial waste rather than post-consumer waste, which raises additional issues related to contamination levels. Regarding organic recycling, there are also challenges in the collection phase. Although legislation imposes this obligation, only 26% of the material in Europe is actually collected, despite the significant economic potential associated with it. Finally, the proportion of compostable plastic in organic waste has been also considered problematic in some facilities. Added to this, the presence of greenwashing with product label as compostable that in practice are not ultimately compromising the quality of the final product. And it's everything from my end. Thank you.